Since the dawn of civilization, we've looked up to the heavens and wondered, how special is the Earth? Does this planet represent the only seat for life, the only place where self-aware collections of atoms ponder who and what they are? Or is the Earth just one drop within a larger ocean, a universe full of worlds teeming with life? For millennia, this has been a question limited to abject speculation and philosophical musings, but not one of serious scientific inquiry. But now in the modern day, with all of our technical powers, our statistical tools and our telescopic arrays, could humanity finally answer a question which has haunted us since our very beginnings? How common are Earth-like worlds? Humanity has wondered how special our planet is since antiquity. Although many religious schools taught that the Earth was unique, there have always been opposing views. For example, the ancient Greek philosopher Metrodorus of Chios speculated that the Earth was akin to a single grain amongst a field of millet. But those ancient schools of thought were really just speculation. There was no evidence to point at and use to guide their reasoning. It wasn't until the mid-20th century that science finally began to take seriously this question as to how common are planets like our own. In 1961, Sir Frank Drake famously reasoned that the number of communicative civilizations in our galaxy could be estimated by multiplying a series of parameters together. If we knew the value of each of these parameters, then we would be able to calculate a direct answer. Thanks to decades of astronomical observations, the first term in Drake's equation, the rate of star formation, is now known to reasonable precision. Having crossed that term off the list, astronomers started to shift their attention to the next term. This is the fraction of stars with planets, which is then followed by the number of habitable planets per system. These two terms are often combined together into a single quantity, usually dubbed eta Earth, the number of habitable planets per star. The eta Earth term is eminently observable, whereas some of the other terms in Drake's equation, such as the lifetime of a civilization, are far more difficult for us to imagine being able to build an experiment to actually observe. But when it comes to eta Earth, in principle all we have to do is look up to the sky and count up how many Earth-like planets do we see. And so institutions like NASA have pursued this approach vigorously, designing their long-term astronomy strategy to first pin down eta Earth and then perhaps eventually go on to tackle the next term in Drake's equation, the fraction of habitable planets with life on them. This philosophy motivated the construction of the famous Kepler mission, a 95-centimeter space telescope designed specifically to measure eta Earth, the frequency of habitable planets, and thus advance Drake's equation by one new parameter. Kepler was launched in early 2009 and enjoyed a 6-month extension to its primary mission, followed by several years in a second life observing different parts of the sky for even more planets. Make no mistake, Kepler was a revolution. Altogether, it observed over 500,000 stars, detected 2,700 new exoplanets, as well as an additional 3,300 candidate signals still awaiting confirmation today. This means that amongst the confirmed exoplanets that we currently know about, over 2/3 of them were discovered by this one 95-centimeter telescope. And yet, as hugely successful, revolutionary, and groundbreaking as this telescope was, when it comes to its primary objective to determine the frequency of habitable planets, that remains a controversial and undecided issue. Now, that statement might surprise some of you. In what way is it controversial, you might ask? Because chances are you may have previously read headlines like this from the Washington Post saying that NASA estimates 1 billion Earths in our galaxy alone. And when you read that, there's no uncertainty in the headline. There's no maybe, there's no controversy. It's presented as if it is a settled issue and no doubts remain. And yet, why am I sat here insisting to you that this remains a controversial topic? After all, if you read it in a newspaper headline, it has to be true, right? Okay, well, rather than relying on newspapers, let's turn to the peer-reviewed scientific publications on this topic and see what they report instead. Now, Kepler didn't really finish its primary mission until 2013. But that didn't stop astronomers from trying to estimate Eta Earth as far back as 2011, where we get a value here of about 3%, or 0.03 habitable planets per star. Over the next 3 years, you see a series of papers which estimate similar numbers, even when the full dataset becomes available. But since that time, the numbers have diverged, with Eta Earth being reported as high as 124%. That's more than one Earth-like planet per Sun-like star. So this gives us a range of over a factor of 100. And so you might be asking yourself, how could it be that astronomers working with the exact same dataset can end up with answers which differ by a factor of 100? As an analogy, imagine that I asked these same researchers to go away and count up what fraction of the population are able to dunk a basketball. You wouldn't expect them to come back to you with answers which differed by a factor of 100. And it's not as if one team is getting an answer which disagrees with the rest. Each team can point to another as an example of someone who approximately agrees with them. One possible explanation is that the teams are not agreeing on how to define what a habitable planet really is. To come back to our analogy, it would mean that they don't agree on the minimum height necessary to dunk a basket. Some teams might be using 6'3", and others might think the minimum is 6'6". And so when they make their counts, they're actually counting different things. And actually the same is true for a habitable planet. A habitable planet is usually defined as that which lies within a certain range of orbital separations from the star and has itself a certain range of physical sizes. But crucially, it's actually very rare for these different research teams to use the same criteria. Consider first the range of allowed orbital distances for habitable planets, often dubbed the habitable zone. In the solar system, Venus is thought to be too close to the Sun, giving rise to scorching temperatures and a runaway greenhouse effect. Mars, on the other hand, is too distant, meaning water is frozen and locked up in polar ice caps. And so the Goldilocks Earth is clearly habitable, but how much could we move it around and keep it that way? Early work used a wide range of orbital distances, labeled here by the associated orbital period in days. Rocky planets found anywhere between the red and blue lines were classified as habitable, and thus would go on to count towards Eta Earth. But leafing through the different publications, we encounter at least 10 different definitions for this critical zone. This situation is then exacerbated by the issue of planetary size too. Early work considered anything between 80% to twice the size of the Earth sufficient to be called a habitable planet. But going forward, very rarely do we see teams actually use the same size range, with now 8 different definitions existing in the literature. So, What is the right habitable range for planetary size and orbital separation? What is the true criteria that we should be using? Well, frankly, we don't know. And likely it's going to be impossible to conclusively give you an answer to that question until we start detecting life on those worlds. For instance, if I detected life on a half-Earth-sized planet, then I could confidently assert that half-Earth-sized planets are indeed capable of supporting life and thus should be classified as habitable. But until we get to the point where we can do that, we are really just guessing about this question, and thus you can unfortunately expect a lot of disagreement about this going forward into the future. With all of these different definitions floating around for habitable planets, we can now easily understand how it could be that everyone might arrive at different answers for E to Earth. But is this really the resolution? Does this factor completely explain the differences between each team, or do they still disagree with each other even after correcting for this effect? Fortunately, there is a way that we can make a fair like-for-like comparison between these different studies and really disentangle what's causing these differences. But in order to do that, we're going to have to switch from our E to Earth term to gamma Earth. Now remember that E to Earth was defined as the frequency of habitable planets around sun-like stars, and gamma Earth is different. Gamma Earth is more like a rate. In fact, it is defined as the rate of planets per logarithmic unit of radius per logarithmic unit of period. Now on paper that looks like a very confusing definition, but we can actually easily understand the difference between Eta and gamma Earth by considering here another analogy. Let's imagine changing Eta Earth from the number of rocky planets within the habitable zone to the number of gas stations we pass in driving from the inner to the outer edge of that same zone. This is the number that we are ultimately trying to measure for Drake's equation. It's how many opportunities for life are there, or here, how many opportunities to fill up our cosmic car that we have. Okay, so what does the gamma Earth represent in this analogy? Gamma Earth here would be the rate of gas stations along the road. So in other words, it's the number of gas stations per mile. Let's say gamma Earth was 0.1 as an example. So if the habitable zone were, say, 100 miles across, then we would expect 10 gas stations in this region. Now what's happening in astronomy is that everyone is effectively disagreeing about how long the stretch of this habitable zone road really is. Some teams are using 100 miles and others are using 200 miles. And so clearly if you double the length of road, then not surprisingly, you come across twice as many gas stations, or in other words, habitable planets along your journey. And so even if everybody is disagreeing about what really makes a habitable planet habitable, in other words, how long that stretch of road really is, everybody should agree about the rate of gas stations along the road, in other words, gamma Earth. And so rather than compare the Eta Earth values, it's actually far more useful here to compare the gamma Earth values. Going from 2011 up to this year, we can see how this value compares between each study. Despite comparing the exact same quantity measured from the exact same dataset, there are still wild differences between the teams. In fact, the estimates vary by a factor of 140 altogether, and even after narrowing in on recent years, we still see a large spread of a factor of 15. And honestly, it is jarring to see some of the world's experts and applied statistical methodologies to astronomical datasets disagreeing with each other using the same data by such a large degree. So what's going on? How can they be arriving at such different answers? Let's say that we observed 100,000 stars and detected 10 habitable planets. On the face of it, that would seem like Eta Earth should just be the ratio of those two numbers, or in other words, 0.01%. But actually, that's certainly lowballing it, as Kepler can only detect planets which are aligned to our line of sight, giving rise to an eclipse or transit event. And so for every Earth-like planet that we see transiting, there's around another 100 which don't have the correct alignment, and thus we need to adjust for this effect. Multiplying everything by 100, all of the team should now agree that Eta Earth is about 1%. Now, in that imagined example, we considered that we had 10 habitable planets, which would be a decent haul. But in reality, that's not what happened. Kepler only found one planet that was within 20% of the Earth's size and orbital period. That's Kepler 452b. Now, one detection is not much to work with. It's very uncertain what the true rate really is. In fact, we would actually say that the number of detections was 1 plus or minus 1. Even so, we can take that one detection, divide it by the 100,000 stars that we observed, and then multiply it by a factor of 100 to correct for the non-aligned systems, and that gives us a rate of about 0.1%. But that number is surely too pessimistic because, of course, Kepler is not a perfect telescope and could have easily missed many Earth-like planets hiding amongst those stars, cases where the noise just overwhelms the signal. In fact, it turns out that Earth-sized planets at the Earth's orbital period are right on the hairy edge of what Kepler is capable of detecting. In fact, even Kepler 452b has come under scrutiny and criticism recently as perhaps not being a real exoplanet at all. Let's say that Kepler 452b is real though, just for the sake of simplicity. And let's further imagine that for every real Earth-like planet that we detect, another 50 are still hiding in the data undetected. So that would mean that there was about 50 habitable Earths with the right alignment, and now we multiply that by about 100 to correct for all the misaligned planets, and we would end up with 5,000 Earths scattered amongst our 100,000 stars, or about 5% of the sample. But slow down for a second, where did that number of 50 even come from? How do I know that it's 50 and say not 5 or 500? Well, that point right there is basically where a lot of the disagreement is coming from. If you think that Kepler is a near perfect telescope, then that one habitable Earth that we have detected essentially represents the entire sample, and thus you would conclude that Eta Earth is a very small number. If, however, you think that Kepler is very inefficient, that it actually misses many, many Earths despite them really being in the data, then you would multiply that number of one habitable planet by some large number and end up with a much more optimistic estimate of Eta Earth. And so really it comes down to how efficient do you think Kepler really is? And clearly astronomers right now do not agree on this. Sometimes astronomers looking at this data try to give themselves a bit of help by assuming that the occurrence rate of planets is a smooth function in period and radius. And sometimes they even assert that they know precisely what that function is. Now, critically, those are strong assumptions, and they tend to overwhelm the constraints presented by that one single true detection. And that's because the vast majority of Kepler's 5,000 detected planets are shorter period, larger planets. In essence, some of these teams have been taking the population properties of these closer in, larger planets and extrapolating them into the window where Earth-like planets live. And it's deeply unclear what the correct method of extrapolation really is. All we can really say is that what you choose for how you do that extrapolation clearly has a very large impact on the final answer. This is most apparent when we compare these two estimates for gamma Earth. These two use the exact same data reduction, but just elected to use two different but perfectly reasonable methods of extrapolation. Nevertheless, they end up with an answer which differs by a factor of 6. Now, none of this disagreement would have likely happened had Kepler been a near-perfect telescope. In that case, it would have detected even smaller planets than the Earth at even wider separations than that of the Earth. In that case, I think everybody would have agreed. But the fact is that Kepler ends up with this fuzziness in its detection ability right at the sort of zone that we most care about for Earth-like planets. And because that fuzziness is in fact very difficult to quantify, we end up with these wildly varying estimates for Eta Earth. I would say that the best way to interpret these numbers right now is that Eta Earth is conservatively 1%, but it could in fact be much higher depending on your assumptions. Now, I know that's not very satisfying, but it really is the best we can say right now. Put bluntly, the question of our own world's uniqueness is still very much unresolved. Now, I want to offer two caveats to the story that I've offered you so far. The first is that all of the numbers I presented in this video have only been for Sun-like stars. We haven't talked about M-dwarfs at all. M-dwarfs are by far the most numerous types of stars in the universe. They are smaller than our own sun, and in fact it appears as though they have even more rocky planets in the habitable zones of their stars than Sun-like stars do. But we really don't know how hospitable they are for life. There's in fact a great deal of uncertainty and debate right now about whether these worlds are even capable of having life on them. The second caveat is that headlines like that of the Washington Post's are performing a second extrapolation on top of everything else that I have discussed thus far. That is because they tacitly assume that the frequency of Earth-like planets is essentially the same across the entire galaxy. But it's important to remember that Kepler only looked at one tiny patch of the local galaxy, and I am personally deeply uncomfortable with extrapolating that rate out to across, say, the galactic core or the outer rim of our galaxy. Now, it does seem as though there are indeed many millions of habitable planets on this basis, but it might not be numbering in the billions. Now, I appreciate that it might seem frustrating to hear a video like this, to hear that astronomers can't even measure this quantity that maybe you thought was a done deal. But it's important to remember that detecting an Earth-sized planet is an incredibly challenging technical feat. When the Earth passes in front of the Sun, for instance, it only blocks out 84 parts per million of the brightness of our star. And so it took space telescopes lofted up above the atmosphere with the most advanced optics and instrumentation that we could muster to even have a chance of detecting these things. And although Gamma Earth is swinging wildly between the different studies right now, the same thing actually happened for Hubble's constant, which describes the expansion of the universe. Early estimates were in fact way too high with large uncertainties, but over the years, the figures were revised and eventually consensus was found. And finally, one big topic that I deliberately didn't get into in this video is what does it really mean to be an Earth-like planet anyway? So far, we've really just sort of called it something with the same sort of period and size as that of the Earth. But are there additional criteria about plate tectonics, a magnetic field, a large moon, a nearby gas giant? Let me know what you think down below in the comments are the criteria for being a truly Earth-like planet. So thank you so much for watching this video, everybody. I really appreciate all of your guys' time. If you like this video, then please do all of the YouTube things. Make sure you hit subscribe, you share this video and like this video, and that just lets YouTube know that science videos like this are valuable and should be present on this platform. So we really appreciate it if you do that. So whether we are adrift in the universe as an isolated, single Earth-like planet, or whether we are just one grain amongst a field of millet, I'll see you all in the next video. Stay thoughtful and stay curious.